Well, I reached out to Sage to see if he was going to be able to make it today, and I have not heard back from him, so maybe he's got a conflict. So maybe we should just move ahead. Oh, here we got Radek, so maybe just another 20 seconds and then we'll start. All right, I'm moving on. All right, so let's see. This week for pull requests, not a ton of new stuff. The only thing that I noticed in my list this morning was a PR I had actually submitted for kind of a first step toward doing priority-based caching in BlueStore, and I'm hoping maybe eventually the OSD. The idea here is, well, maybe I'll get to that later if no one else has anything they want to talk about. But the basic idea is that it's really difficult in master right now for users to set ratios of how memory should be used for different things in the OSD and specifically in BlueStore. Right now, we allow you to kind of specify how much memory should go to metadata in BlueStore, data in BlueStore, and RocksDB's block cache. And even inside RocksDB's block cache, you potentially have the option of specifying high priority and low priority pools for kind of how much memory you want to devote to guaranteeing that indexes and filters remain in cache. And so we allow you to set at least some of those ratios. And then beyond that, we also allow a minimum value to be set for the key value block cache. And kind of when you what we found out was that essentially when users try to do this, it's really not clear at all how all of this interacts. And kind of on top of it, we actually have currently in master a bug where we tend to favor the metadata cache over the data cache kind of beyond what the user specifies. It's not always a bad thing because actually it turns out that favoring metadata cache kind of helps performance in a lot of scenarios and usually doesn't hurt it even when you might expect it to. So it's kind of inadvertently doing a better thing, but it's not doing what the user requests. So it ends up being really, really confusing why things are set internally the way they are, kind of given what the user has specified. So this PR tries to make it on one hand really, really straightforward when the user is specifying ratios and does not enable any kind of auto tuning of the cache, that it just does what the user requests, and it is just setting the ratios to what the user asks, and that's it. There's a flag now where you can enable auto tuning, and then kind of through a more complicated scheme, it will try to make better decisions about where memory should be assigned, and then eventually revert back to those user-defined ratios if it can't if it doesn't think it can do better. So that's it in a nutshell. Beyond that, there were a couple of things that closed. There was a fairly small PR from Igor that fixed something with allocator pruning. I don't think that was super complicated, but good. This async messenger PR from Haomai that that kind of improves the locking behavior merged. Kifu merged that. That potentially is really good for kind of latency related scenarios. I don't know that we've done any kind of extensive testing on it, but at least the testing that was done there makes it look like it's a good PR. And then there was this other one, continue recovery optimization for overwrite ops. That did not merge. It was just closed by the author. I'm not entirely sure why, but I guess for whatever reason that was closed. A couple of ones that were updated. Igor's new bitmap allocator that he presented last week. Sage reviewed it. Looks like he really likes it and wants to replace the old bitmap allocator code with Igor's new stuff. So that's good. Expect at some point soon here that we will have a new bitmap allocator implementation that works far better than the old one. So that's exciting. There's this librd throttle PR. I don't really know too much about it, but yeah, I guess that one must have gotten updated. I should probably figure out what's going on with that. Anyway, yeah, don't know too much about that one. And then Radoslav's work on the crypto SSL PR here, and that's going through testing and getting fixes, and it looks like it's making progress, so that's good. There's a couple that haven't seen movement that are newish. This disk write coalescing by Peter. Some of the stuff from Adam looking at hashing. He's been working on that. I think the latest I've seen is that it's that kind of Sage's more restrictive version of it is working and helping. So maybe it doesn't need quite as much as Adam had originally proposed. So that's good. I think a user is involved in testing that. Another one from Peter about reducing buffer list rebuilds during write-ahead log writes. Radix, huge pages, PR, more stuff from Adam, or sorry, Kifu, I guess in this case, regarding AES and crypto. Yep, that's about it. Don't see anything else real recent here. So that's it for PRs. Does anyone have anything that they would like to discuss this week? All right. Well then, I can go over what I've kind of got and where I'm planning to go with the priority cache if folks are interested. I see Josh nodding his head, so maybe I'll do that then.
Yeah, sounds good to me.
All right, let me see if I can share my screen here. I don't really have a real presentation made up or anything, so I'm just going to go through the stuff in the pull request. Folks see this?
Yeah, looks good.
Okay, cool. So I kind of earlier on gave an overview of the problem here. Right now it's really complicated for users to adjust all of our cache settings. It became clear when we went through some of this with one of our customers. Beyond just the fact that it's kind of confusing, it's really difficult, even if you know what all of the different ratios do, to figure out what they should be set to, and it kind of changes depending on the workload. Everything that I have seen indicates that for like an RBD workload, if you can keep everything, all of the O nodes for BlueStore in the metadata cache, that is the kind of number one priority. It's less clear what happens once you can't do that anymore. If not all of the O nodes fit into cache, maybe you're better actually doing like a full swap over to RocksDB's block cache, because theoretically you can keep all of the O nodes in block cache in an encoded form rather than reading them directly out of memory with BlueStore's O node cache. The the trade-off, right, is that when you're reading from RocksDB's cache, you have a lot more work to do. You're copying memory around, you're doing an encode step to put them there, and you're doing a decode step to get them out. So it's higher latency, more memory traffic, just overall more work that's involved. Obviously, the most work is actually going to disk and fetching them off disk. So at least if you can keep everything in cache, that's kind of what you want to do. There's kind of a bad in-between state where it looks like if you don't have enough metadata cache and you are doing reads from disk, we end up double caching a lot of data. So you end up putting the exact same data that is in BlueStore's metadata cache in RocksDB's block cache. It's not clear whether or not you get some added benefit by doing that. Like sometimes you're maybe hitting stuff in RocksDB's cache that you're not hitting in BlueStore's metadata cache. I haven't really gone through and done an exhaustive look at like the hit rates to determine that, or even like a per onode trace of where it's hitting in what cache. But just from the performance results and from the behavior that's showing, it looks to me like, generally speaking, it doesn't work that way. It looks like either you're hitting BlueStore's cache or you're fetching from disk, or at the very least, the overhead of getting things out of RocksDB's cache is so high that fetching from RocksDB's cache is not really much better than just fetching it from disk in the first place. So that kind of is the conundrum right now, is what do we do in all these scenarios? Kind of the good news is that we can at least avoid some of it by saying, well, if we aren't using a lot of KV cache yet, and if we have memory available, I guess actually if we're not using any of these caches up to that ratio that we specify, potentially we don't need to allocate that much memory to any of them. We can say, well, we've allocated 40% of our cache memory to RocksDB's block cache, but we're only using 5% of that right now. So split it up between the data cache and the metadata cache, depending on what each one needs. And this PR is kind of designed to do that, not just at one level, but to assign a series of priorities where you can say, at this particular priority level, it's important to try to first cache things at the ratios that we've set. But if there's still memory available, then let's give any cache that wants more memory for this priority what memory we have left before we move on to the next set of priorities. So in that way, we can say, if for high priority items, we want more metadata cache beyond, say, like the 1/3 or the 40% of the cache that we specified in the ratios, well, let's give it to that. Let's give it to the metadata cache then, before we give lower priority items a shot at that cache. So that's basically what this does. Right now in this PR, we don't really make use of those priorities very well. The only thing that's specified as high priority right now are the indexes and filters in RocksDB's cache, because if those end up paging out, it's kind of bad. Every time you do a write in BlueStore, you are looking up metadata in RocksDB to see if certain data is already present related to that object. And so the Bloom filters and the indexes are really, really good to keep cached so that we're not doing reads from disk on every write for those. And it's not that big. It's small enough that, that especially for like an RBD workload, is minimal. For an RGW workload, especially with many, many small objects, it actually does grow pretty big. So that's a scenario where potentially if you did not specify a large KV ratio with a limited amount of memory, you might be better off increasing that ratio as the number of objects in RGW grows. So let's take a look here. This is essentially the old behavior of the current behavior of master under an RGW workload like that. You can see that we have kind of a couple of different ratios that are set here: 40% KV, 40% meta, 20% data. So RocksDB's block cache is getting 40% of that 3 GB total cache. The BlueStore metadata cache for onodes and onode related stuff is also getting 40%, and the data cache for objects in BlueStore is getting 20%. In reality, that's what we've allocated, but in reality, that's not actually what gets assigned. Right now in master, BlueStore kind of tries to do some kind of auto tuning itself, where you can see the yellow line for data actually spikes way up at the beginning and then drops back down. And at the beginning, we kind of start out without much meta cache, but it spikes up. If you notice, the amount of data that is allocated is over the course of this run is actually larger than the amount of data used. That's kind of that bug that I was talking about, where we tend to not actually assign as much memory for the data cache as the user specified, and we over allocate memory for the metadata cache versus what was requested. It's not necessarily bad for performance, but it's kind of confusing, because even though the user said that they wanted 40% of the cache for metadata, it turns out that it's closer to like 48%. So anyway, there's that. As we move through this test, we're not using all of the cache right away. It kind of takes a while before the KV cache fills up. So eventually we hit 100% cache utilization, but it's not until about an hour into this test that we get there. This test is writing out 256 gigabytes of RGW data to one OSD, the 16 kilobyte objects. So very small objects, probably about the smallest that you'd ever expect to see in RGW. I mean, theoretically they could be smaller, but it sounds like this was kind of roughly about the smallest that we had really realistically seen customers putting into RGW. Okay, in master, or sorry, with this PR, if we have the auto tuner disabled, sorry, we're switching to RBD now. Maybe I'll actually go down and show the RGW behavior, because that was what we had just talked about, and then we'll go back to RBD. Okay, so for RGW behavior, with the auto tuner disabled, it's really similar to master, except that we fixed this issue where we're under allocating data and over allocating metadata. So again, you can see really similar behavior. It's hitting the user specified ratios. We are not doing any kind of auto tuning at the beginning, where we're kind of taking some of the metadata cache and assigning it to the data cache and then having it shrink back down. That kind of has now been moved into this auto tuner design, so that if you specify that you want auto tuning, it does that, but otherwise it just does exactly what the user requests and doesn't fool around with it. I think personally that that's kind of, if the user is specifying they want these ratios, then we just give it to them, and it's kind of up to them to muck around with them. So anyway, that's very, very similar behavior to what we saw previously. I also ran tests looking at different ratios for the KV block cache, the metadata cache, and the data cache. And again, you can see here that we're hitting all of those ratios really quickly. In this case, actually, we're filling up the cache much faster, because the metadata cache is able to fill in quicker. One thing I will note is that it's not real apparent here yet. You'll see it in the RBD results, but we're actually double caching a lot of the same metadata and Onode data in the metacache and in RocksDB's key value, in the block cache. A lot of the same data is basically being populated in each. Okay, so now with the auto tuner enabled, you see really different behavior, right? Again, you see that the data cache spikes way up. As opposed to master, we're not just doing this for blue source caches. With a couple of changes to RocksDB's cache, we are able to expose some of the information that they have internally about the high priority pool and low priority pool, and how much memory is being used there. So now we can actually try to allocate just a little bit more memory than is used at any given point for these. So that's kind of what we do. You can see that for the key value line here, the blue line, essentially we're always just allocating a little bit more there than is used over time until we get to the saturation point at which everything kind of hits, the allocations that we specified. We're also fully utilizing the cache much sooner than we did previously. One of the things that you'll notice too is that at the crossover point, kind of around 1 hour in, previous to that, we were assigning more metadata because we had it available. Both data and metadata are able to kind of use memory that was assigned to the key value store or to the RocksDB's metacache, but because there wasn't that much memory being utilized there yet, we could give that to the metadata cache and data cache. But at that crossover point, then we kind of revert roughly back to the user specified ratios. The difference being that now with high priority, we are caching RocksDB's indexes and filters. And over time, those are growing because we're just adding more tiny little RGW objects. And so you can kind of see here that, in fact, the amount of memory that's allocated to the key value store block cache grows over time. So it's a little bit different, and it's not entirely clear that we want to favor the block cache in the key value store beyond making sure that those indexes and filters are always cached. It might be that that's a really high priority thing, but beyond making sure those are cached, we're still better off giving the rest of the memory to the BlueStore Onode cache. That's kind of the next step in this, and I'll talk about that more later. But for right now, the behavior currently is that we kind of revert back to the user-defined ratios, except for the fact that RocksDB's indexes and filters are given high priority over other things. And you can see that too when we specify different ratios here, that we're sort of keeping to the user-defined ratios once we hit cache saturation, except that, again, the RocksDB indexes and filters are getting the first shot at memory and growing over time, such that we're sort of sticking to our ratios, but we're also letting the auto-tuner make sure that those things are cached with high priority. In terms of performance, unfortunately, none of this really affected RGW performance at all. There was a little bit of change, but it's such a small amount that it's possible this was just random variation. I'm curious as to whether or not maybe we have enough other latency in the stack that kind of the effective reading from RocksDB's block cache or from BlueStore's Onode cache is really not significantly different than just reading off of the NVMe drive, or sorry, in this case, the SSD drive directly. You can see the latency here is relatively high, not ridiculously high, but high enough that it might be that those reads from the SSD kind of are a relatively minor part of this. So anyway, that's kind of what we see with RGW right now.
Mark, I wonder if you have data about that RGW benchmarking, how many objects there are, and like with the node size, how many nodes would fit in the cache, for example? Like, are we just overflowing the cache entirely there?
Yes, we have gotten to the point in these tests where we cannot fit O-nodes into the memory assigned to the BlueStore cache, and we cannot fit all key value data into RocksDB's block cache either. And obviously, we can't fit the data into the data cache. That's the first thing to go. So yes, in this scenario, we are contending on everything.
Okay.
Which is kind of why we're reverting back to the user-specified defaults.
Right.
The next step in this, I think, is going to be really interesting, where we now look at recent kind of binning of the cache items. So say in the last 5 seconds, we cache the KV cache and the metadata cache with high priority and try to assign everything that's wanted there. And then we kind of do these steps where we go through and look at older and older stuff and try to, divvy stuff up. And I think that will be really important here, because then it will start telling us how much of the recent things are are block cache items versus BlueStore metadata items, and maybe we'll start being able to divvy it up a little bit better. I think also another really interesting thing to do would be to differentiate in the different block caches OMAP data versus ONode data that's also potentially cached in in BlueStore's metacache, because we might be able to start doing some smart things there too.
Yeah, that's a good point. And I wonder if that might be more beneficial for hard disks, for example, to keep the um, even the encoded data around, since there's more CPU to spare. That's kind of
Yes. Yes, I suspect so. All of these tests have been done with SSD just because I'm really paranoid about making sure that none of this has such high CPU overhead that it starts slowing things down beyond, kind of just doing the kind of, most simplistic or dumb thing. The right now the auto tuner is working at like 5-second resolution. It's every 5 seconds it's going through and rebalancing the caches. The next step in this potentially could add some overhead to trim in the cache, which is a little more scary. But I think the auto tuner itself, kind of, as long as you're not having it do work too often, is hopefully not going to impact things too badly.
Mm-hmm.
You said with hard disks, since the amount of work being done is so much lower, potentially you could even do this more often and have it not really hurt things too bad. Okay, let's look at RBD. This is kind of the more fun one. Okay, RBD behavior with auto tuning disabled with this PR. I did not grab graphs of master, unfortunately. I thought I had, but I didn't grab the data about what it was doing, unfortunately. So I don't have master, but essentially it's going to look a lot like this, except with kind of that bug that we've mentioned, where we're not quite assigning as much data cache as we should and over assigning metadata cache. But otherwise, it should look really similar to this. What you're seeing here at the beginning is a pre-fill stage where we are filling up the RBD volume with 4 megabyte objects just to make sure that there's data already allocated there. That's that kind of initial slope to the metadata used and kind of overall total used at the beginning here. At some point, we actually, at maybe, 700 seconds roughly, we actually hit the limit of how much cache we can assign to the metadata cache, how much memory you can assign to the metadata cache. And so now things are getting swapped out. That's where the meta used line kind of goes horizontal. Once we've totally filled up the volume, then we start random writes. And all of a sudden, you see that KV used spikes way up. And that is because we are now doing reads from disk of some of the O nodes. And it's populating both RocksDB's cache and BlueStore's O node cache. And so you see the total use spikes way up, and now we're utilizing all of our memory. But in reality, we're actually double caching a lot of stuff. There's a lot of data that's in RocksDB's KV cache, which is just the exact same data that's in BlueStore's meta cache, and just not being accessed because it's any kind of reads are coming from the meta cache. Theoretically, maybe some of the reads can hit the RocksDB cache rather than going to disk after this. The data that's in the block cache should be smaller because it's encoded using the variant encoding versus BlueStore's O node cache, but it doesn't seem to really have a positive effect. The cost of doing those reads seems to be high enough that it would have been better just to allocate more memory to the meta cache. We'll see that when we look at the performance results, but essentially that's what's happening there. That's why you see that huge spike in the KV used line there. Around probably the 4,500, 5,000 second mark there is when we're switching over to doing random reads. The amount of memory in the caches doesn't change dramatically at all. There's a little bit of a spike down, but not anything, not a spike, I guess a little bit of a dip down, but nothing really there. All you can really infer from that is that's where the random reads are starting. Okay, so what happens then if we don't use the auto tuner, but instead specify that we want a lot of the cache devoted to metadata cache? That works really well. That's actually what we've kind of ended up doing in the last year or two, is devoting most of the memory to metadata cache because the performance results were good when we did that. The reason for that appears to be that, at least in a lot of these tests that we've done so far, where we've got maybe 256 gigabyte or even 512 gigabyte of RBD data, it lets us keep all of the O nodes in cache when we specify a high meta ratio. You can see that here. During the prefill stage, we never get to the point where we start trimming data from the meta cache, and we make it all the way up through the prefill stage and into the random write and random read stage, and the meta used remains constant. And this is the sign that will tell you that that we're double caching above, is that the KV cache in this scenario, the block cache in RocksDB, never grows. It stays really, really small. It's like hovering right around 1% of the total cache. So like 1% of 3 gigabytes. We never actually use that space, though, that could have been assigned. We've over allocated the meta cache. We only ended up needing around 51% of the total cache to cache O nodes, but we overdid it in this particular scenario. If we had 512 gigabytes of RBD block to cache, then we wouldn't have. Then we would have actually underallocated a little bit. But at least in this exact scenario, we've allocated more than enough, and we're not utilizing any of that extra memory that we allocated. One of our partners was playing around with these things, trying to utilize memory in a reasonable way. They had a lot of spare memory. They had enough to give like each OSD 20 gigabytes of RAM, and they did so, but they were confused when the OSD wasn't making use of it, and they didn't understand why. I think this graph right here explains it. When we don't have enough O nodes to utilize the ratio that's been specified, we just don't use the memory. We're definitely using as much data as was specified, and the KV didn't grow at all. So we're not really using as much KV as there, but we're really especially not using as much meta as was specified. Nevertheless, this graph in this particular test, the graph that represents this test, in this test, we saw higher performance than the previous one, where we split the ratios more evenly. And we're using less memory to do it. But we're not really effectively using the memory that the user specified. All right, so now what happens with auto-tuning enabled? Well, with auto-tuning enabled, we're making much better use of the cache right away. The amount of metadata that's needed for the meta cache to cache O nodes grows as the number of O nodes grow. So as we write out blocks to RBD, that grows and then stays constant once we've saturated it. The amount of data spikes way up at the beginning as we have plenty of available memory, and then drops back down, but it drops down to a ratio much higher than we specified. The user specified 20%, but with the auto tuner, it knows it can give it more, so it actually ends up giving it around 42%. And KV doesn't grow because we never enter a state where we need to double cache. If we were writing out a gigabyte of RBD data, then we would. And then we'd enter a scenario where we'd end up having to revert back to the user specified defaults, again, with the exception that we'd be caching indexes and filters at high priority. Right now, that's the behavior, but we can do much better than this PR in the future using the priority scheme, I believe. You'll notice that in the next graph, where the user has specified very, very different ratios, again, 10% KV, 85% meta, and 5% data, the auto tuner converges on the exact same solution. At the very beginning, if you look right around time 0 up to time 100 maybe, the ratios are very, very different. That's kind of an initial idle state where we're just recording data about what the cluster is doing before anything is written out. Those ratios are the user-defined ratios. It's reverting back to those things. It's not really doing much differently. It's slightly off, but it's pretty close. In the previous graph, those ratios, again, are roughly what the user defined, just slightly different, but really close. But then as soon as we actually start writing any data out, it quickly converges back to the same solution. So I'm excited about that. That's telling me that this is trying to be smart about making sure that the cache is well utilized. So that's personally, I like this. I really like seeing this behavior. And in the RBD performance, it looks pretty good too. The worst performing solution by far is when we have tried to not equally, but when we have tried to divvy up the cache equally between the block cache and BlueStore meta, and then giving the data cache some, but not quite an equal share of versus the other two. It does not do particularly well. When we move over to still not doing any kind of auto tuning, but giving the metadata cache most of the memory, so that we're not entering that double cache scenario with RocksDB, it does better. It does pretty well actually. It's still not caching as much of the BlueStore data as it could, but this is all random writes and random reads. So being able to cache 1 gigabyte of data roughly versus maybe I don't know 100 megabytes or 200 megabytes of data compared to a full 256 gigabyte pool of data to be drawing from, it doesn't help the reads that much. It helps a little bit, but not a ton. The auto tuner though does really well in either scenario, no matter what ratios were specified, because it's converging to that same kind of optimal solution. It's actually faster for random writes than either of the non-auto-tune scenarios, and it's faster for random reads, certainly than the kind of suboptimal worst case scenario with the auto-tuner disabled, and arguably faster, at least kind of with the ratios being set reasonably. I don't think there's actually much difference here. It's probably just random variation. I suspect that all three probably perform roughly equally when O-nodes are always in the meta cache. Latency, the 99th percentile latency improves too. The biggest, by far the biggest difference was when we were doing O-node reads from disk or from RocksDB's cache versus when we weren't. The auto-tuner does a good job of avoiding this. We avoid it relatively, well, we avoid it when we have enough meta cache. Again, there might be a little bit of advantage here when we're not, or when we have a higher percentage of the reads coming from the data cache, which the auto-tuner kind of lets you do, but it is hard to say whether or not it's really dramatically improving things yet in this particular scenario. So that's kind of RBD. That it looks like all of this is helping RBD more than it's helping RGW right now. But I think especially as we improve RGW's behavior with Beast and maybe kind of doing other things, looking for other areas where we have bottlenecks. My hope is that this will start also showing more of a performance improvement with RGW like it is with RBD. There are some caveats. Oh, did anyone have any questions on any of that?
So for the RGW bit, this kind of reminds me when we were talking about kind of the caching of BlueStore in general before, and comparing how we were able to get some good results with like local block device caching. And I think we'd seen some good results from the Intel metadata caching layer, I forget what it's called. But that was even with RGW. And I'm wondering if that's because it was using much larger RGW objects, so there was enough or small enough metadata that it would actually fit all in the cache at that point, or if the access pattern was more skewed, so you had a smaller subset of the metadata that would fit in the cache at least.
Do you remember if those tests were done in FileStore or on BlueStore?
Fairly certain they were file store.
Yeah, my guess is that has a lot more to do with PG splitting behavior over time and kind of the fragmentation that you end up with in the directory structure and having to do a lot of fragmented inode reads on the disk, because over time you end up with data from multiple XFS AGs all in the same directory. As you split farther and farther, you start out with all of the objects in a particular PG directory are in the same AG, and they're all kind of located similar to each other on the disk. But as you do splits and kind of mix all of this stuff up, you end up with files, object files that are spanning many different locations across the disk. And so all of those inode reads end up, kind of being scattered. Does that kind of make sense?
Yeah, that does make sense as being a much bigger performance hit, I guess.
If Intel's thing could cache all of the inodes on the SSD, presumably then you could do all that really, really fast and it wouldn't matter anymore.
Right.
That's just a guess, but I have a feeling that probably plays at least a moderate part in why they saw those kinds of results. I'd be really curious how much their software helps BlueStore, especially if you're already putting OMAP data in on the SSD, with the DB on the SSD.
Yeah, that would definitely be pretty interesting. I think when we discussed this before, we were talking about how perhaps the local block device caching wouldn't have as much of an effect once BlueStars caching was more intelligent, because the major effect was from caching that metadata.
Yep.
And if we can do that explicitly, maybe the local block device cache isn't effective anymore.
Yeah. I think I don't know for sure. Maybe I'm wrong on this, but I really suspect that we could do smart caching in BlueStore by having BlueFS allocate space on an SSD just for hot stuff, hot data, right? That could be, instead of reading directly from the block device, it could move or cache hot things on the SSD beyond just having the DBs there. I think we could do that in a way that would be beneficial in different ways than our cache tiering is.
Yeah, possibly. Um, I think at any point when we try to do the data caching, though, we end up being really workload dependent and only affecting workloads that are highly have high time locality.
I think maybe what would be interesting there is if we end up in these scenarios where we don't have kind of enough data cache, which is pretty common, right? To cache all the data that's being written or read for really hot things. Maybe that would be a benefit. But I guess when you think about, like, say, RGW bucket indexes, that's already OMAP, right? So it's already going to end up in the DB already on the SSD. So maybe it's not as big of a deal. Maybe it doesn't really matter that much. It'd only be user, object data that really would benefit from it.
Mm-hmm. Yeah, that might actually make more sense for RGW, because there's less likely to be a caching layer in front of it, whereas like RBD and CephFS are going to have at least the client-side caching in like a virtual machine or a page cache.
Do we have any use cases where we have any kind of client-side code that depends on really, really hot data that doesn't have client-side cache, like maybe with the RBD kernel interface or something?
I mean, the kernel interface typically will have a file system put on top of it, so it still ends up using the local page cache in the client there.
Yeah.
I think maybe some kind of cases with RGW where you don't have any. I mean, you could put a cache layer in front of it, like a CDN sort of situation, perhaps.
What about like a database that doesn't use the file system, that just uses the block layer?
Well, at that point, the database probably has its own cache as well, because it has to replace
Yeah.
the page cache.
Yeah. So yeah, maybe just getting OMAP is good enough. Maybe we don't need to do anything like that. Or maybe just the benefit of it would be really unclear.
Yeah, yeah.
Well, okay. So anyway, caveats of this, again, this is coarse grained. It doesn't happen that often. Right now, I'm just doing it every 5 seconds. I think we could probably increase that a little bit, but we don't want to be doing this probably with every trim. So it right now over allocates a little bit to give itself some leeway to grow things. That's why in some of these graphs, it's not quite getting up fully to the 100% ratio, because it's always leaving itself a little bit of room to grow in case, like, say, the KV used kind of starts going up. It always wants to stay ahead of it if it can. So that's why it's kind of left a little bit of the cache unutilized for future growth. So that's one caveat. Let's see. There's some really weird behavior in RocksDB where uh, by default, RocksDB allows it will grow the block cache beyond the user specified ratios, especially during compaction. The alternative is you can disable that, and it can make operations fail, which I think we probably can't do currently. Um, so, so the gist of it right now is that RocksDB may use more memory than it's been assigned temporarily, especially during compaction. What's a little odd is that when that happens, it appears to completely flush the high priority pool. So all of the indexes and filters get flushed. It only happens when it exceeds the block cache size that's been specified. I don't know why that is. It doesn't make sense to me. So at any event, that's what it appears to do. In this PR, there's some code to kind of try to work around that by if it all of a sudden the RocksDB cache shrinks dramatically, especially like the high priority cache or the high priority pool, the usage there shrinks dramatically. It doesn't just shrink it to the new value. Instead, kind of the RocksDB priority cache layer in this will say, well, I recently saw this high of usage. Now it's saying this. Here's the watermark for what it was previously set to, and we're going to just shrink this slowly rather than just dramatically drop it and then regrow it slowly. Instead, there's some memory here, so let it regrow quickly if it needs to, and then we're kind of back close to where we were before once we had all indexes and filters populated in cache. So we're working around it right now, but I think ultimately we need to understand why RocksDB does this, and if it needs to do this, or if it's just kind of an esoteric behavior that doesn't really make any sense. Future work, I've talked a little bit about kind of this bend LRU approach. I've got kind of a prototype of it in the works that right now reports or bins the different usages. It was pretty easy to implement, so I'm playing around with that. It does not appear to have significantly high overhead. It does add some overhead to trim in the cache, but it's basically just incrementing and decreasing a couple of int64 values with smart pointers to them. It seems like it's low enough overhead that maybe it's not going to dramatically hurt things, at least not at our current performance levels. We'll see. My hope is that once we implement this, it will allow the caches to rebalance based on the workload. Right now, if you imagine a scenario where you've got lots of heavy RGW writes and then later on do a bunch of RBD, small random writes on the same cluster, you still might end up in this double caching scenario because RGW sort of forced you into it. And now without the ability to adapt, RBD will end up in that same scenario with a bunch of old RGW data cached in the KV cache, and you can't get out of it. With this binning, this priority-based binning, I believe we will be able to. I believe we'll be able to say, okay, there's lots of old RGW data, but we don't care about that anymore. We have a much more high priority onode data coming in right now, so let's cache that instead. And then fit all of the onodes into cache. All of the onode data that was in the KV cache starts kind of going into lower priority bins. That shrinks, and now we're back in our optimal scenario where we're caching lots of onodes and not caching KV data that's irrelevant. That's the goal with it. I think we can get there. Other future work might be to do this at the OSD level. Instead of just looking at a user-defined BlueStore cache ratio, I think we want to instead say, here's how much memory we want to give this particular OSD in general. And that accounts not only for these caches, but things like the write-ahead log buffers in RocksDB and the PG log buffers that are in memory and other stuff that's potentially in memory. Right now, the OSD potentially can use significantly more memory than what's defined here. You give it 3 gigabytes of BlueStore cache, and in reality, like in RGW workloads, we might be using close to 8 gigabytes of RSS memory on the OSD. It's very, very different, and we can't account for everything. There's TC malloc fragmentation. There's lots of other stuff that's going to be really hard to account for, but at least we can get closer. We can maybe get to the point where we're not going beyond what we've specified for the OSD too horribly dramatically. We'll see. I don't know, but I at least think that we can do better than we're doing now. And then finally, let's see. Oh, this is the age-based. Right now, even if we did this kind of priority-based binning, I don't think we're going to totally get rid of double caching in RocksDB. I don't know if we'd entirely want to, but definitely in cases like RGW, I think we want the OMAP data to be prioritized relative to kind of the double cached BlueStore ONode data. We really want, I think, the ONode data probably in BlueStore's cache, and we really want the OMAP data cached in RocksDB's block cache, or at least we want to prioritize it versus ONode data in RocksDB's block cache. So potentially, maybe in the future, we can either create multiple caches for each column family, or at least kind of implement some scheme to give different priorities to different prefixes or something. So that might be another potential future area of work that I think could yield improvements. So that's it. We're more or less out of time, but any questions on any of this? All right. Well, I'm going to stop sharing then. Any last minute things before we wrap up, guys? All right. Well, have a good week, everyone. Thanks for listening. I know it's kind of weedy, but I enjoy it. So thanks much.
Thanks, Mark.
Yep.
Thank you. Bye.